Hello everyone, in this video we are going to see about the cache memory. We know that memory has the hierarchy depending upon the capacity to store as well as to the speed of the access. One such memory which comes after the register memory is the cache memory. Let us see how the cache memory is organized between the CPU and the main memory. Let us define first of all what is a cache memory. Cache memory is a special memory of very high speed. It is used to speed up and synchronize with the high speed CPU. What does it mean is CPU has some speed in working whereas the IO devices have different speed in working. So in order to synchronize the speed between the CPU and the other processors and as well as the IO, there need a in between buffer like memory which is called as the cache memory. This will help to speed up and as well as to synchronize with the high speed CPU. Cache memory is an extremely fast memory type that acts as a buffer between RAM and the CPU. So we know that RAM is the random access memory where all the currently working process will be brought in, and CPU is the processor which can access the RAM to process any program given by the user or the programmer. So in order to maintain the access speed between the RAM and the CPU, this cache memory play a very important role. It holds frequently requested data and instructions so that they are immediately available to the CPU when needed. So whenever the CPU is in process, it needs some data and instructions. Instructions are the programs, are the part of the programs. So we need the CPU need some frequent instructions as well as the data. So frequently requested data or instructions will be fetched into the cache memory so that the CPU can access very fast this information and do the process in a speed manner. Cache memory is used to reduce the average time to access data from the main memory. So as we know that when the memory is fast, the access time is also will be slow, will be less. That means we can fast access the memory. So cache memory plays an important role which helps to reduce the average access time. The cache is a smaller and faster memory that stores copies of the data from frequently used main memory locations. So as we said earlier, the content of data are brought into the cache memory in order to do the faster processing. So the main memory data is brought to the cache memory for speed access. Let us see how the cache memory is placed in between the CPU and the memory. So you can see here we have secondary memory, primary memory, cache memory and the CPU. We know that secondary memory is the slow memory which is the backup memory, and primary is the main memory, and CPU access the primary memory in order to do any functions. So in order to do the functions, the CPU has to access the primary memory for all the data and instructions needed. In that case, a cache memory is brought in between the CPU and the prime memory, and frequently used data is fetched from the prime memory which is again passed to the cache memory. From the cache memory, CPU gets the data and do the process in a faster manner. So you can see here the arrows between all the CPU, cache memory, primary, secondary, everything is bi-directional. That means data can be read in and also will be written afterwards. So it is a bi-directional lines are going between these devices. Now let us see about the cache performance. So when you talk about the cache performance, we have two different terms called hit and miss. When the processor needs to read or write a location in main memory, it first checks for a corresponding entry in the cache. So as we seen earlier, all the data can be fetched from the main memory, and only the CPU can access data from the main memory. Okay, so when it needs the data, it first checks whether it is in the cache memory. If it is not in the cache memory, the system will bring the data from the main memory to the cache memory. So now when the data is expected to be in the cache memory, now when the processor finds the memory location in the cache, it is called as a cache hit. That means we can hit the data in the cache itself. No need to go to the primary memory, which is the main memory. So the processor can access these data directly from the cache because it is available in the cache already. That is called as a cache hit. In case The another scenario is if the processor does not find the memory location in the cache, then the cache miss has occurred. So when available it is called cache hit. When it is not available it is called as a cache miss. So when a cache miss occurs, the cache allocates a new entry and copies in data from the main memory. Then the request is fulfilled from the contents of the cache. So when a miss is occurred, it assumes that there is no data in the cache. So the system will try to bring the data from the main memory to the cache, and then the cache will start transfer data to the CPU, and then the CPU can continue the operation. So now between this cache miss and the cache hit, we have a ratio called hit ratio. The performance of the cache memory is frequently measured in terms of the quantity called hit ratio. These questions will be maybe asked for a one word question. What is the cache miss? What is the cache hit? What is hit ratio? And also how the performance of cache is measured. For these cases, we can answer the questions from here, this slide. So what is hit ratio? Hit ratio is equal to hit plus miss is equal to number of hits by total accesses. So when you have trying to access the cache memory, sometimes we find the data which is hit, sometimes we may not find, that is a miss. So the hit plus miss is the total number of accesses. So the number of hits by total access is called as the hit ratio. Thus this hit ratio measures the performance of the cache. Now let us see. After the hit ratio, we see about the cache mapping. What is cache mapping? So now we know the process here that we always bring the data from the main memory to the cache memory. Main memory is bigger, cache memory is smaller. So in order to locate the data from the bigger memory to the smaller memory, the address of the data from the main memory has to be mapped, has to be translated into the cache address. That is called as a mapping, cache mapping. So there are three different ways of mapping used for the purpose of cache memory, which is as follows. So what are they? Direct mapping, associative mapping, and set associative mapping. So this mapping is classified based upon how the memory lines is mapped into the cache lines. Let us see first of all the direct mapping. What is direct mapping is the simplest technique known as the direct mapping maps each block of main memory into only one possible cache line, or in direct mapping assign each memory block to a specific line in the cache. What does it mean is a line in the cache means an address line of a cache. So the address line of a cache, if we access one address line of the cache, we can access one block of data. That is called as a direct mapping. If a line is previously taken up by the memory block, when a new block needs to be loaded, the old block is trashed. So we know that in the direct mapping, one line of address line maps one block of data. If suppose the line is previously occupied by the memory block, means we have to discard the previous memory block which is not needed. Now we have to load the new memory block in the case of the direct mapping. An address space is split into two parts, index field and a tag field. Now the cache is set to store the tag field, whereas the rest is stored in the main memory. So what does it mean is the tag field contains the address line, and from the address, if it searches the same address in the main memory, it can get a block of the data. So that means the remaining port is a tag field. So the cache is used to store the tag field, whereas remaining are stored in the main memory. So one line of address line will give bulk of data, a block of data. Direct mapping performance is directly proportional to the hit ratio. That means when the data is available in the cache, now it can access the data directly. So this direct mapping concept is mainly proportional. The performance is mainly proportional to the directly proportional to the hit ratio. That means if the hit is more, if there are more number of hits, means the direct mapping will be work faster, will be in a faster manner. So this is all about the direct mapping in cache memory. Let us see how the diagram shows here we can see here a cache memory control logic is here, and up is the main memory, pages are there, and here we are having the CPU. Now the CPU is connected to the memory area, which is having a block of frame having set 0, set 1, etc. up to set n minus 1. Okay. And now here, as we just seen earlier, now here line of this cache memory or the address from the cache will transfer or will help to get a block of data from the main memory, and that will be passed to the CPU. So this is how the direct mapping occurs. Let us see next concept, which is the associative mapping. What is associative mapping is, in this type of mapping, the associative memory is used to store the content and addresses of the memory word. Generally, this associative mapping is also called content addressable memory, which is CAM. Okay. So now what does it mean is, the data itself will be the address, the content itself will be the address. Now with the address we can access the content itself. That is called as, that is the concept of the associative mapping, associative memory. So what does associative mapping means is that, now here the associative mapping means the word itself, the content itself can be fetched by the address in the address itself. That means the content is implied in the address itself. That is called as an associative mapping concept. And any block can go into any line of cache. So here there is no need that first line will access the first block, and so this will be random manner where any block can be accessed by any cache line. That means from the cache, from any address of the cache will access any block in the memory. That is called as an associative mapping. This means that the word ID bits are used to identify which word is in the block is needed, but the tag becomes all of the remaining bits. That's what just we have mentioned here. Remaining will be the data itself. And this enables the placement of any word at any place in the cache memory. That means there is no need to maintain the order of the memory arrangement of the data inside the main memory. It is considered to be the fastest and most flexible mapping form. In associative mapping, the index bits are 0. What that means is, there is no need to have the index bits, because in the previous memory mapping method, which is the direct mapping, we are using the index bit. The remaining tag bit will be the content. Here the index bits are not necessary because we access the data by the content itself. For example, if we have register number of the student, it will be in the order. Okay, and now instead of giving the index bit, we can give the register number itself as the address of the particular block. So if you start accessing from 1, we need the 100 data, means we can just from starting from the first line we can access the plus 100. That means 100 students data can be fetched by the from the register number. So this type of memory comes under the associative mapping. Let us see the block diagram of how this associative mapping is mentioned over here. So we can see here there is a main memory. Now the diagram difference here is the CPU is here, cache control unit is here. Here what we can see is, from the main memory we have the block of frames. So the block of frames can access to any of the line from the cache memory. So that is the concept here. And now every block has one set of data. So now when the cache memory got the address from the main memory to access the data, it will just pass the address line to access one block frame. That block may be any of the block inside the memory. So what does it mean is, if the address which comes from the cache memory matches the address which is inside the associative the memory block, then by the matching between the address which is got from the cache line, the address is matched and then the data is got from the memory. That is called as an associative mapping. There is no index bits. Index bits are 0 here. So next is the set associative mapping. This form of mapping is an enhanced form of the direct mapping, where the drawbacks of direct mapping are removed. Set associative addresses the problem of possible thrashing in the direct mapping method. So what is thrashing is, frequently bringing the data from main memory to cache memory often requires some household work. That is the housekeeping work. So for that housekeeping work, we need more of the memory cycle and the energy from the CPU, or the process or the work from the CPU. So that process is called as a thrashing. So in order to avoid this possible thrashing, which is in the direct mapping method, set associative gives some improvement. Let us see what is that improvement. It does this by saying that instead of having exactly one line that a block can map into the cache, we will group a few lines together, creating a set. So the associative mapping actually gives only one line of information, whereas here we are having set of lines, creating a set of lines from the same address. So by this, what we can do, then a block in memory can map to any one of the lines of a specific set. So this is the advantage over here. So with this type of memory access, a block in the memory can map to any one of them, because we are creating a set of lines from the address given to the cache memory. Okay, so now we can create a group of lines, and if suppose one line doesn't match the content, we can check with the other line. So set of lines, all here line means the addresses. Okay, so if something is not available in one address, it can find out the next available addresses. So when a group of line is mapped, if one line or one address does not contain the required data, this will check for another line to look for the expected data. If the data is not available in the whole set, then only it will going to ask for data from the main memory to the cache memory. So by this, we are reducing the unwanted access from the main memory to the cache memory. So this will reduce the transfer of data often from cache memory to main memory. This is an advantage which is in the set associative mapping. So this combines the logic of direct mapping, which gives one line of data to one block of data, plus the associative addressing, where we are creating a set of lines into a single address, and then we are searching for the expected data from the cache memory itself. Let us see how the diagram looks like. And before that, set associative mapping allows that each word that is present in the cache memory can have two or more words in the main memory for the same index address. So this is what just I mentioned before with an example. Set associative cache mapping combines the best of direct and associative cache mapping techniques. In set associative mapping, the index bits are given by the set offset bits. What is the offset bit is, for example, I am accessing the first element of the array. Now I want to access the 10th element. So what I can do is, address of the first element plus 10 will give the address of the 10th element. That 10 is called as an offset. How much you are going to skip, how long we are going to move, that is called as an offset. Okay. So now here in set associative mapping, the index is created by the given offset bits. In this case, the cache consists of a number of sets, each of which consists of number of lines. As I told you just before, every line consists of one address. So one line of address contains number of sets. That means if we access one line, if data is not available in one set, it will be maybe available in the next other set also. So how does the diagram looks like? You can see the improvement in the diagram before we see the earlier diagram. Again, we can see the main memory is above and the CPU is below. Cache control logic is here. So what does this memory area is now widened is, we can see the block frames. Inside the block we have set 0 and so on. So here many blocks and many sets are there. Okay, so if you access one set 0, there we have so many blocks. In this example, set 0 means here we are having 1, 2, 4, 5, 6 blocks are there. So if you address one set with the set 0, we can access 6 blocks of data. So we can search the data among all the 6 blocks instead of checking once in the previous method, which is the associative mapping. Okay, so that's all the advantage of how the direct mapping as well as the associative mapping is brought together in the set associative mapping. So these are all the 3 different techniques by which the cache is mapped. So mapping is nothing but converting or translating the address from one form to the other form. Here the main memory form to the CPU form, okay, through the cache memory. So now here we can see here, when the main memory contains tag and word offset, cache memory contains tag, set offset as well as word offset. So now tag is divided into tag and set offset. That means the number of bits which is available to tag is divided into two groups, tag as well as a set offset. So if the tag is matched, then only you are going to look for the set. So now by this we can reduce the number of access time. So that's all how the cache is mapped between the main memory as well as the CPU, and the three different techniques of direct mapping, associative mapping and set associative mapping. Hope it is easy to follow, and thanks for watching.